right, we're going to continue with continuity. And trigonometric functions are continuous over their entire domains. And here's a proof. And again, I'm not going to have you doing proofs, but it's good to see where this comes from. I know this is a little blurry, but here we're looking at identities of that you had in trig, and this goes through how can we show that that it is true that the trigonometric functions are continuous over their entire domain. And then here is the proof for sin x, which is analogous because the remaining trigonometric functions, we can express them in terms of sine and cosines, which is pretty neat. Their continuity follows from the quotient limit laws. All right, let's just kind of look at an example here. Find a value or values of k that make the function continuous over the given interval. So let's see how we do that. All right, so here we have f of x equals 3x plus 2. X is less than some value. We're going to try to figure out what that is. 2x minus 3, and x is greater than or equal to k, whatever that value is, and less than or equal to 8. So we're going to look for the limit of f of x as x approaches k from the left. So we have, we're going to substitute our k, and just like if that was a number, we substitute it in. So we have 3k plus 2. Now we're going to do it from the right here, okay? And that should be a plus right there because it's from the right, so that should be a plus. I apologize for that. So the limit as x approaches k from the right of 2x minus 3 equals, again, substitute k in, I get 2k minus 3. For f of x to be continuous, then these two limits from the left and from the right have to equal each other and have to equal the function value at k. So remember, these three things have to be equal. Those are that three criteria at the beginning of the continuity section. Those three have to be equal. Thus, 3k plus 2 must equal 3k minus 3, which k equals negative 5. Okay, so when we solve this for k, we get k equals negative 5. And so that would be the function would have to be continuous. That's the value that would make it continuous. Okay, one last thing we're going to talk about from this section is the IVT, or intermediate value theorem. And it says, let f be continuous over a closed bounded interval. So we're looking at a closed interval bounded by AB, or whatever those values are. If z is any real number between f of a and f of b, then there is a number c in our interval AB satisfying f of c equals z. So remember, z is a real number. So here's let's look at our graph here, our picture. So there's our function. All right. And f of x, our function f of x. We're a closed interval from a to b. Z is any real number between f of a and f of b. So there's z, and it's between the two. If that is true, then there is a number, so there's our function, there's a number c in this interval satisfying f of c. Remember, this is f of c right here, and would equal whatever z is. So that's that intermediate value theorem.